Okay.
I
Questions?
was,
What
yes,
question? Yeah. Yeah.
just one question. I was going to ask in regards to bringing time into the equation.
Yes.
How is the idea of a vector space related to the idea of a phase space? Is that a continuous? It's almost like a vector space with continuous time. Is similar or completely different?
You mentioned the phase diagram. Did you mention the phase diagram?
Yes, phase
Yeah.
diagram. Yes.
The phase diagram is different. The phase diagram is, in that case, you're talking about the two or more dependent variable. How does their relation evolve or
It's a
change
function.
with
Okay.
time? Yes. Well,
Okay.
this,
Okay.
this is similar. Okay. In our case, not to have, we have at least, in our latest example, we have 3 age group. Can you see that?
Yes.
So therefore,
Yes.
the situation is more is equally complete. You can call it a diagram, the phase diagram, by just following that. Can we just go to the whiteboard?
Mm-hmm.
Yeah, go to whiteboard here. Oops, share the space. Share the screen. Ah, that's better. You see, you are mentioning two ideas. It's a space and a phase diagram, right? A
Okay.
phase diagram is all usually used in the when you solve in the multivariable, at least 2 variable time-dependent issues, the system.
Okay.
Okay,
Okay.
and yes, it's relevant, but in our case, it's also the true. So what's the phase diagram? Let's just show you what is the phase diagram. So basically, if you just draw a background. Okay. So the phase diagram is just this idea is related. So this is another idea, the phase diagram. Okay, phase diagram. And what is phase diagram is just if you monitor. Normally when we started the vector, we say the vector just keep the constant. Okay, static.
Mm-hmm.
So
Yes.
this is dynamic. So this phase complete describing is a diagram of time dependent variable or vector, in this case vector,
Mm-hmm.
because if its components became variable, the vector became time variable. So that's the time dependent vector. Can we just emphasize the vector? In our case, the population is time dependent. Do you agree? Every year you change
Yes.
the total population is changed. Okay, this year may be slightly different from next year. Okay, if there is a million of the social upheaval, you will see the dramatic change, like the war, like this natural disaster, for example, right? Otherwise, the total population very smooth, very smooth.
Mm-hmm.
Okay, but still, so what happens that if that is the case, you will see that I still use diagram to show you what would happen. What if I use the vector to describe this total population? Can you see the red arrow? Can you see the red angle? Can you see the arrow? Can you see the arrow on my side? No?
Yes.
I'm moving the arrow. Can you see that?
Yes,
Okay.
I can.
Okay, basically I
Yeah,
make
yeah,
it,
I can see it.
okay, I can make it, I can this much better, can you see? So what changes that
Yes,
when,
yes,
when
looks
the,
good.
you see, the vector change, there are 2 ways to change. One is just no direction, but the length, okay, the amplitude. That's the one variation, okay? Another variation is that the total population not change. Can you see like that? You see that? So this total population just changes slightly, okay? Okay.
Right.
Now
Different weighting.
I'm do this wobbling now. Can you see? I do this wobbling now. Okay. Now I will stop here.
Yeah.
I make this vector stand still. Instead, I will try to memorize. Can you recall the trace or the project how to say trajectories of what we have moving?
Trajectory, yeah.
Trajectory, can you see?
Yes.
Is that trajectory moving? Can you see?
Yep.
Can you see that?
Yes.
That is a phase diagram, okay? That is a phase diagram.
Okay.
That is a phase diagram people are very interested in, okay? Now this trace diagram looks a little bit random, okay? Others, so you will see that sometimes you will see the phase diagram, talking about the phase diagram. So this is just including two population, okay? This is not 3D though. I hope that will help you to understand what is the phase diagram.
No, it does, yeah. Yes.
So for example, can you use population 1, population 2, okay? I just pick up 2 age group, okay? The 2 age group, for example, the teenager and the 20 years old women population is change, okay? The change.
Yeah.
And sometimes, if you're lucky, you will get some different diagram. Sometimes you get this, for example, sometimes you get this. Can we just draw that? Sometimes you get this diagram. Can you see? Sparrow, sparrow.
Yeah.
Okay.
Yeah.
And other time you get oscillation. Other time you get oscillation. You got this one, like a solar system. Can you see?
Yeah.
So that in terms of diagram, there are many possibilities. Okay, and these two examples are depending which way you go. If this go to spiral inward, and we call this is a conversion. You know, diverging and converging. So because eventually they end up with a dot. Okay, it would appear this one bring that trajectory eventually gives a dot at the center somewhere. Can you see?
Is that a what's it?
Equilibrium.
Fixed point attractor.
Yeah, attractor. Yeah, attractor. Yeah, attractor or equilibrium or attractor is a good way. In this case, attractor is there but not reachable. It's just moving around it. Okay. Now there is that if you. I think it's time for us to move to the calculus next time. Do you agree?
Sure.
Because that will give you some. Of course, we'll repeatedly pick up this idea from the linear algebra, okay? Another phase diagram is this, similar to this one, but can you see this time, they just go out, I use the same color. Another phase diagram goes from in, go to outside, can you see? That system is, do you think this system is stable?
No,
it's not
unstable.
Stable. Not oscillate. Okay, that must be happen. That must be some prey and predators competition. People eat each other. Okay, so eventually, you know, the stronger group survive and the weak one dispute. There are many others. Can we just extend another pattern issue like this? Sometimes just this is a very simple one. They just oscillate along the straight line. Can you see? Okay, so there are many phase diagrams. They are not just one. There are many. Okay, all the possible. So what we are studying, the reason we pick up the Nasty metric is because we are starting this continuous. This is continuous. So these are the continuous phase diagram. When you study the mathematics, there are two types of the phenomena. This is called continuous. Okay, other just discrete. Okay, you can, for example, we can study this as a discrete. Can you see? What we can do? We can choose a time, say a time interval, say 5 years or 20 years or whatever you choose. And in this case, they change. This one? Can you see the T1, T0, and the T2 will be here. It's T2, T1. Okay,
and then matrix in between.
That's T3 will be here, T2, and then probably that will be T3. Okay, so same formula. Actually, if you know, of course, that's why I'm asking you. If you want to change, if you want to divide the age into a infinity number group, then you will see the continuous change. Okay. So in other words, when you start to continue, we can always, I can just stick with this diagram. You can study this phase diagram, either use a continuous variable or use a step or discrete. Can you see? We can also study this phenomenon. This is one. Can you see? Can you see? Can this white dot here? That is how we can also study that.
And there's a matrix in between each point.
So there's a Tn, there's a Tn n plus 1. Yes, that's why just return to our basic idea that how do we use a vector to describe the multivariable phenomena, in this case, the age group, okay.
Sure.
So that is when you use this one, you end up with another description called discrete. So that is worth discrete. We use white color. Discrete. When you use a discrete, use a time interval. Use a time interval, size 1 year, 5 year. You wouldn't use fraction of second. It's too small. Can you see that? There's no, if I just draw the straight, can we just draw the curve? Can you just, so for example, when you see the curve in mathematics, when you see the curve here, right? So that implies this is a continuous change of two variables. Okay. In this case, can we say this? Can we call this is say fx? Can you see?
Yep.
This is change. So again, when we study mathematics, we study continuous function, or we study mathematics in general, we prefer to use this Cartesian coordinate. Can you see? Cartesian coordinate, this idea still remain when we study the we are studying space more than 2D. Okay. But if you want to understand mathematics further, and we can always confine to the 2D. In this case, y equal to fx. That would be a variable called x. Okay. So you can consider this x is continually change. Okay. However, you can also study this discrete. Can you see? Yes. We just divide this x into the equal interval. Can you see? Sure. So that becomes x0, x1, x2, x3, and so on. So that's how we if you in terms of time, you can see this is t1. Can you see the t case? So it's t100. Okay, this is t100, 100, 102, and so on. See. So the matrix allows you to actually manipulate the discrete data. Or in other words, we can approximate. That's a good idea. You can so a continuous function. So continuous function. We're talking about variable. Is function can be approximated by using discrete function. That is important idea in mathematics. Okay. Now, when we study when we study the linear algebra, we confine everything into the discrete space. Okay. We cannot talk about the time. We can only talk about the step. Okay. For example, matrix, the basic formula in the linear matrix is that we can we just there's the first page. So that is the idea when we solve the real problem. Okay. Yes. So we know that the time is continuous, right? Time cannot jump. Okay. Time is just continuous to cover every second or fraction or 1/1,000,000th of second. Time is continuous, right? However, when we describe the phenomena, we don't have to use a continuous variable. For example, after all, you only need to predict the stock market daily. Do you agree? Nobody interested in what to be the stock price in the next fraction of 1,000,000 second. Nobody care, right?
Yes, exactly.
So that is a bridge. So this is a very general idea. So we can bridge the continuous function and by using discrete function. And of course, the accuracy is dependent on how to use the discrete function. The more the
Sure.
better. More step is better.
I see. Infinitely, an infinitely small amount.
Yes, so that's why you see when we studied linear algebra, we use matrix, and that is how people start with dealing with the discrete variable, as if the
Yes.
age jump, okay, as if age say this, say this is year 2000, the age is year 2001, this age is 2003, okay. But
Yeah,
that is
sure.
a good way. Can you see if you just can, if you draw this trend line here, you get the same thing. Can you see? If you draw this trend line,
Yes.
you just use different colors. If you draw this trend line, you get the same function. Can you see? That is
I see.
idea.
Okay.
That is idea why we use discrete functions.
I see. All connected.
Yeah, all connected.
Yeah.
So just put one more sentence, one more remark here. So what we are doing is actually we are trying to work out the phase diagram. Phase diagram is also can become the solution. Alternatively, the phase diagram is also the solution. You see, of differential equation. That's okay. I hope. Where is it? Oh, I choose this one. So basically, the phase diagram. So phase diagram also represents the solution to a differentiation equation to a set of a coupled simultaneous differential equation. Have you heard of differential equation?
I have, yeah.
Yeah. Then that is a differential equation is based on calculus. You see, I think shall we start to start some function and calculus next time.
Okay, great.
Now, if you have any question or problem solving, we can return to linear algebra. Okay.
Sure.
But I think these answer your curiosity or your concern, right?
Yeah.
So what does a phase diagram to do with what we are doing? Well, if you follow this end of the arrow, you will see these trajectories. You will see different patterns. You will see this pattern. Of course, fortunately, if you want to draw a more realistic description of the age group change in any state in Australia, then you will see this pattern. So I can see that you can see the pattern is very stable, very stable. So you can see that just to one of them. So it's very close to this one. And basically, if you just follow this particular point here, you will see each group. Okay, each group, I still use same color. So you will see some slightly change next year. Okay. Next year, a group like this, and look like that, and look at that, right? Look like that, and like that. Yes. Yeah, they're not necessarily always a circle, but they're just wandering around this stable. Yeah. So that's why of course, eventually over years, over decade, you will see the population of particular state will increase. Can you see? So in this case, what is going on here? If you use a vector that can visualize this change. So in this case, can you see that is initial? That is initial vector. This initial population says 20 years ago. All right.
Yeah.
And then this is a final. This is a final vector, population vector after say 20 years. Can you see that?
Yes.
So that diagram, each diagram. So each point in this curve or diagram, in this phase diagram, will tell you exactly the breakdown, population breakdown, or the number of each age group. Okay.
Yes.
Can you see that?
Yes.
You can follow that this card. You can follow this dot. You see as time change, this change. Okay.
Yes. And there's a matrix transformation that sums up each jump.
Yeah. Last question. If the population remains the same for 10 years, how to describe this change?
Identity matrix.
Yeah. No. In this case, this just not move. So this vector doesn't move.
Right. So but would you not multiply? It's just a vector multiplied by the identity. It's just by one. It's the same.
Yeah. Right? That's how to work out the components. How to work out the total population by the components. Remember, the population we have constraint. I forget to tell you, the total population I, from any time. So this is a constraint. We're equal to the total population. This is constraint.
Yes.
It's constraint.
Yes.
Okay, we can talk about the detail if you wish to, because I just have the several students finish their population assignment.
Yes.
If you're interested, I can cite some of their results and analysis.
Yeah, that sounds good.
Because after all, eventually you are going to dealing with real problem. Okay, no matter you're doing degree or you actually found it, to do some search, because that is I think it's a good example, because you will see the large numbers. You have to how to group them. They are research skill. How to group them, regroup them, and how to represent them in the vector, and then how to work out the elements for each elements in the linear matrix.
Yes, great.
All right.
Definitely, that sounds good. Well, thank you very much for explaining that.
That's
incredibly interesting. I look forward to talking next week.
Yeah, we'll talk next week. Goodbye.
Okay, goodbye. Have a good day.
You too. See you.